So, well, let's go back to this story, the quantum toric varieties. So they are meant to be thought of as a compactification or partial compactification of quantum tori. But uh, uh, unlike the past, where the quantum tori, the tori was only one algebraic torus, really. Now we have many, many quantum tori that could be partially compactified. So this allows for a modular space of these objects where the deformation parameter is, well, I'm writing it as h bar in this particular example. This is a one-dimensional deformation parameter in this particular example. But of course, in higher dimensional examples and so on, there will be various deformation parameters. Or a multidimensional deformation parameter. We already saw this story. To be more precise as to what quantum P1 is, well, it will be a stack. And if you want just to fix an idea in your mind for now, you can think that this is a sort of an orbifold, sort of. Traditionally, the charts of an orbifold are groups acted on by finite groups, but now it's a manifold acted on by a finite group, but now it's a complex manifold acted on by an infinite discrete group. Say the northern hemisphere of this object. So what does this object look like? Well, let me just try to picture it just fancifully, without a lot of precision. And traditionally, if h bar was a rational number, then we would be having an orbifold. We would have a weighted projective. We would have some sort of weighted P1 that would be with some weights. And we would end up with a weighted P1 with some weights. And then it would look, in the rational h bar case, it would look something like this. Where this cone, well, has an angle having to do with P, and this cone has an angle having to do with Q, and some people refers to this weighted P1 as a football, with this sports metaphor coming from American football, not from soccer. They refer as a football. But of course, now when H is more freely not rational, but rather an irrational real number, then it's no longer a classical weighted P1. You are to imagine this thing as a, well, more fuzzy thing, but it still has two hemispheres. And of course, now the picture is even less precise. Now, well, this is like infinity here and infinity here. So did you have this kind of infinitely thin cones glued somehow? And this is what we're doing here. We have this action of, and remember gamma in this example is the subgroup generated by 1 and h bar inside of R1. So it's just a subgroup of R, an abelian subgroup of R, and And well, this group is acting somehow by translation on R. It acts by translation. Just additive translation on R. The first action of 1, it already makes R mod 1. Already makes it a circle, where we still has the action of the rotation by H bar. That is just a copy of Z acting on the circle, but no longer of Z mod 3 or Z mod 4 when it's irrational, but a full infinite Z acting on the circle by some irrational rotation. And the quotient is a non-Hausdorff space. I'll come back in 1 second. Sorry about that. So we have that situation. This is, well, I said S1, but of course you can extend this easily to C star, and then you'll have and then furthermore, you can extend the action to C, just partially compactifying C star. And then you will get one of these hemispheres. And then, well, then you'll have this kind of infinitely thin cones to form quantum P1. That you may want to think of some sort of generalization of an orbifold. Well, that's interesting enough, but we would like to have a more systematic approach to the whole thing, of course. And again, I'll repeat a little bit about this dimension counting. When you have the torus, and when I draw this torus, now you are to think that this is C star cross C star rather than S1 cross S1. Rather than S1 cross S1. So when you have this torus, the complexification of the torus, you have this complex algebraic group, and you have this foliation, and you are in the irrational case of the foliation. The rational case of the foliation is algebraic and everything is fine. But when you are in the irrational case of the foliation, you really think, if you want, this is T2, just homotopically, just from the point of view of homotopy, you imagine that this is T2 mod R. What you have here, the action of the reals on the two-dimensional torus. Well, that's you have to choose a cathode. We chose the cathode of stacks to make sense of this quotient. But homotopically, R is contractible. So homotopically, the dimension of this is just T2. It's just 2. The dimension from the point of view of homotopy is 2. Of course, from the point of view, geometrically, the naive dimension counting could be 2 minus 1 would be 1. So we have two different dimension countings, two. But you start doing homological algebra, Hochschild homology, all sorts of these typical invariants that you would compute. You would get, they would be comparable with the dimension counting of two. Not with the dimension counting of one. But then there would be an abrupt discontinuity as I move h bar. Because as I move it, sometimes it's rational. And then in the rational case, definitely the dimension is one, and the homotopy dimension is one, and all the dimensions are one. But when it's irrational, then you have this dichotomy where the homotopy dimension is two, kind of the topological dimension is two. And this is very unpleasant, and it causes a lot of troubles for from many different theoretical points of view. People notice this discrepancy. People have noticed this discrepancy in many different various languages. So the way we proceed to alleviate this problem in our theory is to complicate the case H in Q, and to make it compatible with the nicer H not in Q case. Again, H not in Q, even for the algebra associated to the foliation, the convolutional algebra associated to the foliation, is just the algebra, the so-called algebra of the non-commutative torus that we have mentioned before. It's a non-commutative algebra. H bar E. This is 2 pi I H bar YX. This is the famous algebra of the non-commutative torus. But it is secretly commutative. It is Morita equivalent to a commutative algebra when H bar is rational. So we want to make it more non-commutative even in that case. We want to make the whole thing very holomorphically. In the H bar parameter. And it's just not happening the way we think that these leaves become torus knots when H is in Q, then the whole thing doesn't move holomorphically at all, not even really continuously, nothing. So because we want to move the thing holomorphically, what we do, well, this I will mention immediately afterwards. What we do to do this is to consider gerbs. So, if I have the torus and I have the rational case where this thing winds around a number of times, but then it comes back onto itself. In this case, it goes around, once like this, I guess, 3 times like this. This would be the 1/3 case. But it could be any torus knot. If we have that situation where the leaves of the foliation are like this, I'm going to insist that no, they are not circles, the leaves of the foliation. They are copies of R. I'm going to take the universal cover of these torus knots, and I'm going to make a copy of R that winds on the torus over and over, so that the action, so that the action acquires a stabilizer at every point, acquires a Z stabilizer. Every point, at every point of the whole space. So, well, these topologists are classified by these kind of structures. We have this kind of stabilizer all over the place. We say that this is a a gerb with a billion band Z. So if I was compactifying this to make it quantum P1, if it is irrational H bar, well, no gerb. But when H bar is rational, then, for example, when H bar is 0, then I have P1. But I don't get P1 just P1. I get a new P1 that I called in this slide CP01, because I was calling CPH H bar 1, the general situation. So H equals 0. And this lands over P1 with fiber VZ. Well, but VZ is C star. I mean, VZ is just, at the first order of approximation, is just a homotopy type of space. But in the category of states, fortunately, VZ has a realization as a complex manifold, C star. So this is the complex manifold. Essentially, this kind of line bundle over CP1, more precisely a gerb over P1. P1 acquires this gerb, and this gerb is what we are going to call P1. Now, you could complain, but this is not P1, old P1, the ones I used to have. And then I would say, well, there is a way in which it is. If I start developing the theory and I consider the category of toric varieties together with a gerb landing on top of toric varieties, but I forget the toric variety. And I just remember the toric varieties together with a gerb that is totally canonical on the toric variety. The category of toric varieties together with this gerb that I will call calibrated toric varieties is equivalent to the category of toric varieties. So nothing is when there is a one-to-one correspondence between calibrated toric varieties and toric varieties, the categories, and fans, therefore. So there's a one-to-one correspondence between fans and calibrated toric varieties. And so you can have always thought about calibrated toric varieties. There is a canonical way to forget the gerb and a canonical way to recover it. So a calibrated toric varieties contains no more information than its classical counterpart, a toric variety. So I could say, well, the calibration was always there, invisible to the naked eye, but if you look a little bit closer, you see it. So the warning is that classical toric varieties should be thought of in this theory as always coming together with their canonical gerb, and it is totally canonical, even complex analytically, and essentially it comes from the line bundles coming from the divisors at infinity on the compactification, and it's totally canonical. So I insist on remembering this information, and now everything becomes very nice. As I vary H bar, as I vary the deformation parameter, the family of toric varieties, and both in the quantum and non-quantum case, in the rational and irrational case, become a holomorphic family over the parameter H bar, and now we have a universal family, a nice modular space of toric varieties, both at the same time, classical and quantum. By just remembering this, the fact that this is really almost nothing. It's just remembering that this is not a circle, but a copy of R winding eternally on itself. That's all that we're doing. And then the quotient acquires this Z stabilizer everywhere. when I do the quotient. So when I do the quotient, this becomes a circle, but it acquires a set stabilizer everywhere. And then it acquires a set stabilizer everywhere. These sets are ugly. And it just acquires set stabilizer. And because this is Bz over S1, then, well, this becomes, again, a two-dimensional torus. So the correct dimension all along was 2 when I think of the additional calibration. Well, I just remind you the most simple but essentially very archetypical examples. And this archetypical example is the example. Again, CP1 is very archetypical. You already see a lot of what's going on in that case, as you would expect. And in that case, the way to realize all this holomorphic family and everything that I just promised, but I haven't proved, is to notice that a very beautiful classical fact that is that about P1 there is this Hopf surface that is diffeomorphic to S3 cross S1. And this is an important atom of complex geometry. This is a complex manifold. And it almost wants to be, it's related somehow to P1 some elliptic vibration over P1. So it is a bundle of elliptic curves over P1. If I forget this S1, what I would get here is S3 this is S2, then I would get here S1 rather than S1 cross S1. And this is a non-complex analytical nothing. This is a differential topology object called the Hopf vibration. In fact, the Hopf vibration realizes in homotopy theory phi 3 of S2 being Z. The Hopf vibration realizes pi 3 of S2. And it's important in topology. But if I multiply by S1 this, and by S1 this, and by S1 this, then I get, no, just S1 this and this, no, not this. Then I get the complex version of the Hopf vibration. This is kind of the real version of the Hopf vibration. I will get kind of the complex version of the Hopf vibration. Now these are complex manifolds. This is, so S3 crosses 1 is a complex manifold way. But of course, the cohomology of the second cohomology of S3 cross S1 is 0, of course. So it cannot possibly have a symplectic form. There is no room for H to have a symplectic form. So H is not symplectic. Therefore, H is not Kähler. So it's not symplectic, it's not scalar, but it is a complex manifold. S3 cross S1 is a complex manifold called the Hopf surface. It fibers over P1 by elliptic curves. So it's an elliptic fibration over an elliptic family over P1. This is because it's of dimension 2 complex, 4 real dimensions. It is called it's a complex surface called an elliptic surface. And many of these elliptic surfaces, it is well known in geometry, come from something called the log transform. So in fact, H is the log transform of P1 cross E. It's the so-called log transform. The Kodaira's log transform of P1 cross E gives you H. This is H, and H is what I call here NH. NH is simply H, but of course I would want this H is 1. What something is to an arbitrary toric variety. And this something that it will be a complex manifold will be not symplectic, not scalar, but of course it will be not an elliptic fibration, but it will have higher dimensional complex manifolds, complex tori. I mean, this will be some tori that is a complex manifold. It's a 1 crosses 1 crosses 1 crosses 1 crosses 1. Often enough. But this will be called an LBM manifold when I consider a general toric variety. But in the case of P1, is a famous Hopf surface and is the complex version of the Hopf fibration. But every toric variety has its complex version of its Hopf fibration. And this complex version of its Hopf fibration has this thing here is important. It's the LBM fibration associated to the complex manifold X, if X was smooth. But even when X is not smooth, it's an orbital or anything, we still have this situation. So, so far, so good. I have 10 more minutes today, so I'll continue with this a little bit more. So here, well, I can think that H is foliated by elliptic curves. I don't know, here is H, and it is foliated by elliptic curves somehow. And the quotient of that foliation is P1. But if I take the universal cover, of the elliptic curve, this will be P1 together with a germ, because the stabilizers will, again, we'll have a set stabilizer. And I'll germ over P1. I will get calibrated P1. If I take in the universal cover of leaves of these foliations. Also, interestingly, perhaps a new remark now, less well-known or not known remark, is that if I take away the north and south pole here, and I just look at C star inside here, I just took the north and south pole here, and I look what lies on top, well, I get this well, I took something out of these elliptic curves. So I get this kind of complex torus knots inside C star. But anyway, what I get is the Kronecker foliation. The restriction is just a Kronecker foliation on the one component to the one-dimensional case C star. So this compactifies the Kronecker foliation in an adequate fashion. You know, this so this Hopf surface gives us the clue as to how to proceed. Okay, so we do that. So CP1 really is, well, it wants to be the space of leaves of this foliation, when I think of it as a foliated Hopf surface by elliptic curves. And I don't worry right now about the gerb at the moment, and I just ignore it. Well, this compactifies the Kronecker foliation. And, well, we have the Hopf surface on top, and I can also see it like this, like not acted on by an elliptic curve, but by an action of an abelian group. We have this complex analytic abelian group acting on this complex manifold, the Hopf surface, and that gives me. But of course, this was just one possible action. Now I deform the action holomorphically. I just deform the action holomorphically a little bit, and I get quantum P1. I have to tell you exactly how to deform the action holomorphically, and I will. In fact, I will tell you the general story for a toric variety. But anyway, this is the scheme for quantum P1. Now, this scheme translates very well to another with the classical story for another famous example that is taking the toric variety Pn minus 1 cross Pm minus 1, and on top of this we get the Calabi-Ekman manifolds. So these are diffeomorphic to products of two spheres, two odd spheres, but they are complex manifolds. And again, in this case, we get a famous elliptic fibration over this complex manifold, no longer an elliptic surface, and people have proved that these are generalized log transforms, no longer the classical log transform of Kodaira, but generalized versions of the log transform. And in this case, we have the same scheme, you know. We can deform these, and as we deform these by parameters, now more parameters, we get these. This was the analogous torus knot, and in fact, it is exactly torus knots. Lots of torus knots. But as I move this deform this by some parameter, h bar, but now it's a beta, has two components, no longer one. Well, I get the same. It's the quotient would be non-Hausdorff. But now the quotient is, well, quantum version of this. So the quotient literally would be non-Hausdorff. So in this theory, X remains, this thing remains constant. The foliation varies, the group action varies, this remains constant, and the quotient changes. And that's how you deform the toric variety into a quantum toric variety. Now, if we have here a more general toric variety, arbitrarily general, it's over the complex numbers, here we would get an LBM manifold that we will call N. This is our N in this example, classical example. In the case of Pn-1 cross Pn-1, they are called the Calabi-Ekman complex manifolds. They are non-symplectic, non-Kähler, but still complex manifolds. There is this famous complex structure on this product of these two spheres. There is a subtle complex structure. It's non-obvious. Laura Merseman and Alberto Berkowski discovered the corresponding ends, the corresponding, well, they are called LBM manifolds. Lopez de Medrano was involved in the story, Berkowski and Merseman, and now they land over an arbitrary toric variety. So an arbitrary quantum toric variety, or general, there is even more general, but for now, a general toric variety will come from an LBM manifold acted on by an abelian complex algebraic group. This is a complex manifold that is non-algebraic, and the quotient. And this action will be parameterized by some sort of H bar. This will be a foliation. When H bar is rational, it will have lots of torus knots. It will have lots of torus knots. But when H is irrational, well, it won't. And the quotient will be this non-commutative space, or stack X, non-Hausdorff topological space. That will be the quantum toric variety. So that's the scheme more generally. And we got all the way here. And well, the piece of information that encodes this situation is a quantum fan. But I guess I will talk about that next time. Thank you very much. Any question?
Yes. So I don't understand if what you say about this H bar. So it feels like you have only one parameter from what you're saying, but I would imagine that there are more ways to deform than just one parametrically.
Well, here it is, the situation. This is for next time. I'll do it a little bit better. But the parameter of the formation is in the classical case that I was describing, P1, the beautiful P1 case, gamma was 1 H bar inside of R.
Okay. So no, I understand what you're saying, but for example, if you take P1 cross P1, you can deform separately the components. You can deform P1 with one H and other one with another H. So
and even more.
Exactly.
You could have any subgroup of R2, any finitely generated abelian subgroup.
Okay. Okay. Yeah. Well, very interesting.
So, it's any finitely generated abelian subgroup could be the parameter of the formation.
Mm-hmm. Okay.
And here you can see my beautiful handmade art.
Yeah, indeed. It's marvelous.
Anyway.
Thank you so much.
Any other questions?
No, today it was quite clear. So I'm still wondering if you could give some precise computation of homotopy dimension in this stacky case. So I would really appreciate it, but...
Good. Yeah. I'm trying to first give an impression of the theory because it has many details. And then we can do that.